Everything look good?
Yeah, looks perfect. Take it away.
Hi, everyone. My name is Collin Brandl. I'm a PhD student at the University of New Mexico, and I'm going to talk to you a little bit today about some along strike discontinuities in igneous addition, and how those are evidence for what we think is rift to ridge segmentation at the ENAM. And I just want to thank my co-authors first right off the bat, Lindsay Worthington, Bix Magnani, Donna Shillington, and Tom Lucky. So get right into it. So the last supercontinent, Pangaea, broke apart around 200 million years ago, forming the eastern North American margin along the United States east coast, with the opening of the Atlantic Ocean. Normal seafloor spreading didn't seem to start immediately following breakup. Recent results from Shuck et al. In 2019 found a region of thinner and seismically faster oceanic crust between the East Coast Magnetic Anomaly, or the ECMA, and the Blake Spur Magnetic Anomaly, that they deemed proto-oceanic crust. And they hypothesized that this crust was formed from the diffuse upwelling of melt through remnant continental lithosphere, and that normal oceanic crust is found past the Blake Spur anomaly. And the ENAM has been studied a lot in the past, with some sparse margin perpendicular seismic lines, and they imaged two main forms of igneous addition to the margin, seaward dipping reflectors, or SDRs, and high velocity lower crust, or HVLC. The origin of this type of transitional crust really remains unclear. It could have formed like that proto-oceanic crust, or it could be maybe heavily intruded continental crust. And the SDR package is generally thought to be the source of the ECMA, and the ECMA itself is highly variable in the magnitude and the width along strike. And that implies that there should be more crustal structure variations along strike that we haven't seen before. Some of that variability has been compared to mid-Atlantic ridge segmentation, but we haven't had this detailed along strike view beneath the anomaly to know for sure. So we've used some seismic data from the 2014-2015 ENAM community seismic experiment that acquired both onshore and offshore seismic data. Offshore wide angle data was reported on ocean bottom seismometers with shots from the RV Marcus Langseth. We're focusing on lines 4A and 4B here, which are centered on the ECMA, and they intersect near the cusp of Cape Hatteras, North Carolina here. This covers about 375 kilometers of a long strike distance. And here are P-wave velocity models. And for anyone unfamiliar with P-wave velocity models, the colors correspond to P-wave velocities that we've inverted using travel time tomography. So each of these models, we have 5 layers. There's water, some upper sediment, a lower sediment, a basement, and a mantle. And we really see pretty minimal along strike variability in the sediment layers, except for some high velocities that we attribute to some salt diapirism. But we're primarily interested in this basement layer that should contain both the SDRs and the HVLC. Now, for most of the models, the velocities right above the MOHO reach about 7.5 kilometers per second, which is what we would expect. But we see these two locations where velocities only reach about 6.9 or 7 kilometers per second. And we're calling these HVLC gaps because of the lack of high velocities. And these gaps are also coincident, approximately coincident to the extrapolated locations of the Cane and the northern Cane fracture zones from the mid-Atlantic ridge. I said lines 4A and 4B, they intersect. So we stitch them together to create this full along strike view beneath the anomaly. And when we're interpreting this, we don't see a reflection that distinguishes the SDRs or the upper crust and the lower crust. So we're just dividing them based just on the velocities. So when I'm talking about SDRs, that's basically from the basement reflector to the 6.7 kilometer per second contour. Then we're talking about HVLC, it's from about the 7.2 kilometer per second contour to the mantle, or to the MOHO. And we first looked at some potential field data just to see if there might be any along strike correlations, and neither our total basement thickness or the average lower crustal velocity correlate with the magnetic anomaly. That makes sense because the SDR package should alone be the magnetic source, not the entire basement. We do see an interesting correlation between the average lower crustal velocity for these HVLC gaps where the velocity dips and the gravity anomaly. And that might be expected. If there's a reduction in the velocity, then probably is a reduction in the density as well. And that seems to help verify that these gaps are a real feature and not just a modeling artifact. So our first big question here is, can we constrain the origin of the crust beneath the ECMA? And to do that, we first looked at the 1D average velocity versus depth profiles for crust with HVLC, the solid line, and the HVLC gaps in the dashed line, to a sampling of other kinds of crust. So here we're looking at the proto-oceanic crust I mentioned from Shuck et al. In 2019, the sampling of stretched continental crust from Christensen and Mooney, and to some continental crustal profiles from Eastern North America. Now, when all of these profiles are hung from the basement, the crust with HVLC seems to plot or look like maybe slightly faster and slightly thicker proto-oceanic crust. But the HVLC gaps sit somewhere in between this proto-oceanic and these continental profiles. Now, if instead of hanging them from the basement, if instead we align them all at their respective mohos, that crust with HVLC still resembles thicker and slightly faster proto-oceanic crust, but those HVLC gaps almost exactly match the lower continental crust from Eastern North America. So it looks like that crust with HVLC could have formed the same way as the proto-oceanic crust from this interesting kind of seafloor spreading. But is that true? Could that crust form entirely from a mantle melt? So any igneous addition to the margin we expect to come from a mantle melt, and we've used some mantle melting models to compare the necessary conditions at lines 4A and 4B to some established conditions. Now, in these models, any combination of mantle potential temperature, upwelling ratio, and the pre-existing lithospheric thickness results in different lower crustal velocities and igneous crustal thicknesses. Now, that Shuck et al. Paper in 2019, they used a similar approach to constrain the conditions for the proto-oceanic crust, and those are plotted for reference. So on the left here, we have a calculation using a pre-existing lithospheric thickness of 6.7 kilometers. That was the best fit for line 1 from the ENAM CSE from Shuck et al. And on the right, we have a plot using a pre-existing lithospheric thickness of 13.4 kilometers. That was the best fit for line 2. As I said, if that crust with HVLC is just thicker and faster proto-oceanic crust, we can use our total basement thickness for this igneous crustal thickness, because everything should have formed from a mantle melt. Now, if we do that, the crust with HVLC, this red ellipse, it plots across a pretty wide range of mantle potential temperatures and upwelling ratios. An analysis of the Central Atlantic magmatic province basalts, they've indicated that the mantle source is likely near 1450 degrees C, and there hasn't been any evidence of active upwelling documented at the ENAM. Now, I'll also note that the HVLC gaps, I can't even plot them in this space because the velocities are so low, and that seems to indicate that they probably can't be formed from this kind of mantle melt. Now, alternatively, I mentioned we could consider that this crust with HVLC wasn't formed like proto-oceanic crust and instead is heavily intruded continental crust. And in this case, we can calculate the igneous intrusion thickness in the lower crust just based on linear mixing of the velocities. So we did that, and the residual igneous thickness is 2 to 5 kilometers thinner than the overall basement thickness. Now, if we use that calculated intrusion thickness, these are the same plots from before, but with that calculated intrusion thickness, now our high velocity lower crust, it plots almost exactly along passive upwelling in the same temperature range, which makes a lot more sense for what we've seen at the ENAM. And the HVLC gaps still can't be plotted, and that kind of verifies that they definitely can't form from a mantle melt in any capacity. So are there any implications of this for the volume of igneous addition at the ENAM? Now, in Holbrook and Kellerman in 1993 estimated a total volume of igneous addition at the ENAM of 3.2 times 10 to the 6 kilometers cubed. And they used the cross-sectional area from 2 tomography profiles, and they multiplied that by the total margin length. And they acknowledged that this was likely a maximum overestimation because of the assumptions they made. In 2020, Green et al. Used or modeled the magnetic source of the magnetic source thickness of the ECMA for the entire margin. And then they used a SDR to HVLC ratio of 1 to 3 that was compiled by Gallahue et al. To estimate the margin volume. Now, this newer estimate was 1.6 times 10 to the 6. That's a 50% reduction from the Holbrook and Kellerman estimate. But it relied on this ratio that might be different for the ENAM. So we found that if we use our total basement thickness, that our SDR to HVLC ratio is closer to 1 to 2 instead of 1 to 3. And if we just use that ratio with the Green et al. Estimate, the total volume is reduced to about 1.1 times 10 to the 6 kilometers cubed. That's a 31% reduction. And as I mentioned, if we believe that the lower crust represents heavily intruded continental crust. So if we use that intrusion thickness I mentioned, our SDR to HVLC ratio is closer to 1 to 1. And that reduces this volume even further to about 8.4 times 10 to the 5 kilometers cubed. That's a 48% reduction from this Green et al. Estimate.
Collin, you had 10 minutes now.
So is there some explanation for this along strike variability? It seems like it has a big effect on a lot of different aspects at the ENAM, but what could be going on or what could be causing it? So I've shown that there are these along strike discontinuities in igneous intrusion, that the HVLC gaps are most likely unintruded continental crust. And those HVLC gaps appear to be coincident to mid-Atlantic ridge fracture zones. Now, this implies that there might be a connection between that along strike variability and the mid-Atlantic ridge segmentation that others have been looking for with just the anomaly itself. So our preferred hypothesis is based on fracture zone formation modeling in the Woodlark Basin done by Taras Gurria. Now, in this model, we have separate magmatic centers at the continental rift, and they have heavy intrusion and surface volcanism that seems to cover the rest of the crust indiscriminately at what the intrusion level is. Now, as these magmatic centers transition to seafloor spreading with the rift to drift transition, we have these crustal bridges that are trapped between them. Now, eventually, as this new formed spreading center, it wants to reach a stable configuration. And as it does that, these crustal bridges will break apart, but still stick out farther seaward than we would expect. So we have these, we've been trying to figure out a good term for them. My favorite is this like toe, someone's calling it. We have this, basically this piece of unintruded continental crust that sticks out farther seaward than the average rift to drift transition position. And if we took a profile from A to A prime to A double prime with a similar geometry as that we have for lines 4A and 4B, we think we would see a crustal structure that looks like what we're observing at the ENAM. We would have some heavily intruded continental crust that would be the HVLC adjacent to basically unintruded rifted continental crust that would be the HVLC gaps. And those are adjacent to these fracture zones, the Cane and Northern Cane. And that would indicate that the along strike variability we see at the ECMA is related to segmentation of the continental rift, and that from the continental rift transferred directly to the mid-Atlantic ridge. And then just to wrap things up, so the crust beneath the ECMA is highly variable along strike, and there are these newfound gaps in the high velocity lower crust. Sections of crust with HVLC are most likely heavily intruded rifted continental crust, and the HVLC gaps seem to be unintruded rifted continental crust. The volume of igneous addition could be up to 48% less than the most recent estimate, if what we're seeing at Cape Hatteras is consistent for the entire margin. And that lower crustal that along strike variation in the lower crustal velocity structure, it looks like it reflects segmentation of the early Pangean rift that then directly transferred to the mid-Atlantic ridge. With that, thank you for allowing me to give this talk.
Excellent, Collin. Very fascinating. There are a few questions. Cynthia, you're first.
Just a quick question about comparison to the seismic velocity structure, say in the AFAR, where in the previous talk, it would clearly indicate we know the process, we have an idea of the amount of intrusive to extrusive and their relationship to SDRs. Had you thought about looking at that or just comparisons with offshore marine data sets?
I hadn't thought about comparing that, but actually that is something, we just got some reviews back on this paper, and that was one of our suggestions, was to maybe broaden our velocity comparison. So I'm definitely interested in doing that to see. My original intent was just to try and nail down if those HVLC gaps were just the lower crust from North America. But yeah, I am interested in comparing it a little more broadly now.
The paper you mentioned by Taras for the Woodlark Basin, he also had a paper, so as a as a co-author for AFAR. That might also be an obvious link to follow up. Kim, you have a question.
Hi, Colin. Thanks for a great talk. I'm kind of curious, in terms of your velocity model, I mean, clearly that was, you were inverting for travel times as well as MOHO reflections too.
Mm-hmm.
And for your PMP, do you see a variation in the character of the PMP when you go across those supposedly unintruded versus intruded bits?
Not particularly. Or that was the wrong direction. No, that was something I actually had originally hadn't looked at, and I had tried to do a little bit of an examination on the amplitudes or anything, and I never really saw anything that stood out to me as any like character variation.
Okay, so like versus sharp versus more like diffuse and hard to pick, or they're kind of all the same?
It seems like they're all the same for the most part.
Interesting. Thanks.
There's one more question in the chat, but that's a convener, so that doesn't count really now. Ritzke, you have a question.
Yeah, hi, Colin. I mean, interesting observations, but I don't really understand this. In your cartoon-like summary, you imagine that there's basically a segmented drift with offsets, but we don't see those offsets, along strike offsets, in the observations, and also not in your cartoon D. So I'm a bit puzzled. What has happened with those offsets? I mean, why don't we see basically a stepping margin going from south to north in the along the margin, and what's happened in your cartoon D with those offsets?
That's a really great question, and I think that well, to be the simplest, honest answer, I think that was just a poor job of me in my conceptual model of my cartoon making. I think that so in the woodlark and the terrace is done, it seems like that those offsets were necessary to form the crustal bridges. And I agree. I haven't observed anything at the ENAM that that looks the same as that. And I think there's still some work to be done about trying to determine if this model is the perfect model that explains those crustal, or that, I guess, the toe, I'm just going to call it the crustal toe, those pieces of crust that stick out. Because the other thing that this model seemed to fit what we were observing the best, but obviously the Woodlark Basin is a significantly less magmatic rift than the ENAM is thought to be. So there already is a slight mismatch there. But I think this is probably one of our biggest places we still need to add some work to really develop a model that fits what we're observing.
All right, that's okay. Thanks.
Okay, now Fola, it's your turn.
I was already trying to type my question, but I'll just go ahead. So thanks for the question, for the nice talk, Colin. So my question is about the result from certain studies along rifted margins, that in the later stages of rifting, when you have intense stretching and thinning of the crust, and with the crust has lost most of the strength, you really don't have inheritance from that part being carried over into the newly forming oceanic crust at continental breakup. And I've seen some other studies that try to associate pre-existing weaknesses in the crust and this rift transfer or interaction zones controlling transform fault location within the oceanic crust. So and I see you're trying to make a connection between that model here in this image right on the screen, rift segmentation zones directly connect or influence transform faulting. So I want to know if you have any thoughts about those other studies that imply that you should not have much influence of crustal structures being carried over into transform fault formation.
Good question. I'm unsure. It's like I guess I was trying to get at with the last question. This type of modeling obviously isn't my specialty, and is something what we would really, I would like to nail down to, obviously find out exactly what processes are going on at the rift that lead to these. I think that it's in my mind, it's such an obvious coincidence that the fracture zones are located right next to those HVLC gaps that I think there has to be some kind of relation to them. But yeah, I think there has to be something there. I'd really like to get, push it further and see what we can actually come up with as a definitive answer on the inheritance or not too.
Thank you.